Good day, everybody. And today we're going to continue our series on calculus. And today we are at implicit differentiation. We would have already looked at the power rule, we look at the product rule, we would have looked at the chain rule, and most recently the quotient rule. So today we're moving on to implicit differentiation. What is the aim for today? What is today's objective? Basically, to be able to differentiate various functions implicitly. So what we would have done so far in this series, all the functions that we would have differentiated by the various strategies, the various means, they were all explicit, simply because we were differentiating in respect to one unknown variable, which was the x. In this case, when we deal with implicit differentiation, what we need to understand is that differentiation is taking place, but we are differentiating two distinct variables in respect to one of them. So how do we know when we have to differentiate implicitly? Simple. You will see more than one variable within the same question. So here, for example, you have x and you have y. And y here is not necessarily the subject of the formula. So in a case like this, this is when we perform implicit differentiation. And there are many ways to go about it. I've seen, for instance, cases where we would make the y the subject of the formula and then we just differentiate. Yes, that could work, but most so importantly, I prefer to use it as is just to bring across the concept. And there is honestly no easier way to explain how to do the implicit differentiation than by doing an example itself. So we're going to work with this same example that we have here. 2x plus y is equal to 4x. The whole idea behind implicit differentiation is this. You are generally when you differentiate a function, you differentiate in respect to x. So we perform regular differentiation, power rule, if power rule requires. Sometimes it will call for the product rule, the quotient, or the chain rule. But whichever means we choose, we differentiate normal. However, whenever we differentiate a y term, we just have to attach to that y term our dy dx, or in this case, I'm going to use y prime to denote that differentiation took place. And then after we do our differentiation, we simply make y prime or dy dx the subject of the formula. I'm going to do this one as an example so that we could follow. So here, to differentiate this entire thing here, I could simply use the power rule. So here what is happening? I differentiate 2x. When I differentiate 2x, I will get just 2, right? Now, that will be plus. I'm differentiating the y. When I differentiate the y, I will get 1. And I will just put it for now, but just so you realize that we don't really need the 1. And because I differentiated a y term, I attach a y prime. This simply means that I differentiated y. I would use y prime, but similarly, you will see sometimes you use dy dx. And believe me, if I could have write better, I would have used dy dx. But it's a lot easier to write y prime with my current technology available. So whenever you differentiate a y term, that's all you do. You put dy dx or y prime in my case here, and then you continue. So this is equal now to 4x, and when I differentiate 4x, I will get 4. Notice when you differentiate in an x term, there is no need to put dx dy because we are actually already differentiating in respect to x. But when we are differentiating a y term, we have to put the y prime or the dy dx because we are differentiating y in respect to x. And that is why it's important to put that. And as long as you understand that, that is all there honestly is to differentiating implicitly. So here, if I do this, of course, I have my y prime. And now, as I said, the next aim is to make y prime the subject of the formula. And in this case, let me remove the 1, just to let you know that that one is not necessary. It's understood. And in this case here, to make y prime the subject of the formula, all I need to do is move this on the other side here. And that would leave me with y prime is equal to, and I'll jump the gun here, 4. At this level, I think we all could see what happened there. So the 2 is positive here. When we go on the other side, it'll be negative. So it's 4 minus 2, and that will leave us with 4. Good. And on the side note, I just want to do it on the side here just to let you know that sometimes you do have this option, not always, but sometimes this option presents itself. In a case like this, in a function like this, it would have been even easier, forget the implicit differentiation, and it would have been even easier if I simply make y the subject of the formula and then differentiate. That is plausible with this given function. So I could have moved the 2x on the other side, and notice the answer would be the same. So here I could end up with y is equal to 4x, good, minus 2x, good. My answer would not be interfered with. This would be the same as 2x, yes? And last but not least, then when I differentiate my y, I will end up with y prime, and that y prime would have also been equal to 2. So this is just another option. If you're very good with algebra, if you're very good with making the subject of the formula, you could actually maybe sometimes save yourself from doing implicit differentiation if you could make that y constant or variable, the y unknown, the subject, and then you just differentiate. But I'm telling you, not all the time this presents itself like that. So instead, just remember the rules. The rules is as simple as just differentiate as normal, but whenever you reach a y term, you differentiate it, but then you attach to that a y prime or dy dx. When you finish with your differentiation, then you just go ahead and you make the y prime or the dy dx the subject of the formula. Sometimes, of course, you will require to put them together or whatever not. Let's see. Let's do some example and see if, as they present themselves, let's see if we can explain them. So here we have here we have 3 examples. We're going to do all 3 of them. Of course, this is the part of the video where if you understand the concept, you could pause it, attempt them on your own, and see if we get the same answers when we finish. So let's do some. I'll do them right now. So here we have the first one. We have 4x squared is equal to 2y squared minus 3y. And again, as I said, the concept is very straightforward. So I will just start by differentiating. Remember, differentiating as normal, whether you might have to use the power rule, quotient rule, product rule, chain rule, again, that's for you to figure out based on what is presented. And here, as it is presented, all this can easily be differentiated using the power rule. So how do I go about doing this? Using the power rule here, I will end up with 8x, we have to remember the rules, 8x. So that's the answer there. That's this one is differentiated. This is equal now. Notice on the other side I have 2 y terms. So when I differentiate, I have to remember to attach my dy dx or my y prime. So here I have 4y. That's what when I differentiate, remember the 2 goes in front. I multiply the 2 by the front and I minus 1. That is simple power rule. So we have 4y, and then to that we attach y prime. Yes, because I just differentiated this y in respect to y. If you want, you could even put your dot there to symbolize multiplication is taking place between these two. And then you have minus, I differentiate this in front here. If I differentiate 3y, remember I'll just end up with a constant. So I'll just end up with 3. And to the 3 now, I attach my y prime. Easy does it. And that is basically the ending of my differentiation. But I ain't finished yet. Now I have to make y prime the subject of the formula. How do I do this? In this case, I'm moving on. So I have 8x. And in this case, I could factor out y prime. Yes, so if I factor out y prime, I have y prime. And inside the bracket, I have 4y minus 3. Yes, this is sometimes where it gets tricky, finding a way to differentiate, not a way, finding a way to isolate the y prime. Sometimes that could become very tricky. I could tell you that in advance, especially when written as dy dx. Yes, it could confuse a lot of us. So y prime is equal to this. And of course, to make the y prime the subject of the formula, here on, I just have to divide by 4y. I divide by 4y minus 3. And of course, what I do on one side of the equation, I also do on the other side. Basic high school stuff. I also do on the other side of the equation. So this 4y here will cancel this 4y here. And ultimately, that will leave us with the answer. And I'll just change around a little here. y prime, I like my answer on that side. I think I would have expressed that in the past. Y prime is equal to 8x divided by 4y minus 3. And that is my final answer. So the first derivative of this implicit differentiation will be y prime is equal to, or dy dx. Remember, y prime is the same thing as dy dx. It's the same thing. If you look online, this is probably how you more likely see it, dy dx. Or likewise, it's the same thing as f prime of x. It's a function of x. So that's all. All this is saying the same thing. Y prime is saying this, y prime is saying this. It's just a matter of notations and representation, but it's the same thing. Good? And that's what we have here. So when we differentiate this y prime here, we end up with 8x divided by 4y minus 3. And in this case here, let's see. I'm looking at the possibility of making y the subject of the formula. And believe me, when I say in this case, it would have been a very hard task. Yes, it would have been a very hard task to isolate one of these y's to be the subject. So yes, this is why, again, the knowledge of implicit differentiation could make our life a lot easier. Because this wasn't really hard. If you really agree with me and you understand what I did here, it's not really hard. And that's basically differentiating implicitly. Sometimes when, again, as I said earlier, it may not be possible to really make y the subject of the formula. So in a case like that, yes, you just have to go the road of differentiating implicitly. Good. Let's go on to the next example. So here we had example number 2. Here we have 3x squared plus 3y squared is equal to negative 10. And again, breezy, easy breezy. I start by differentiating. So the first one there, I would have 6x, remember the 2 goes in front, so that's 2 times 3, that's 6, and then 2 minus 1, that's 1, and the 1 is understood as a power. And I differentiated at x, so there's no need to add an extension. Here now, I am differentiating a y. So remember, once I differentiating a y, I have to attach my dy dx or my y prime. So here my answer would be 6. When I differentiate this, I will end up getting 6y. But to that 6y now, I attach or multiply that by y prime. Simply because I'm differentiating a y term. Because we are differentiating in respect to x. So that's why when we differentiate the y, we have to attach our y prime. And our negative x, our negative 10, sorry, will simply become 0. Because remember, anytime we differentiate a constant, it becomes 0. And that's what it is. Good. So moving on, and from here now is just to clean up. So we're making y the subject of the formula, and this one is not too bad. So here we have 6y. So 6y prime is equal to, let me put a multiplication sign so we know that multiplication is taking place here. So 6y prime, 6y, y prime is equal to negative 6x. Yes, negative 6x. Remember, I just got this here on the other side. Simple transposition. It's possible, it's positive over here. I said possible. It is positive over here. So of course, when I bring it over, it becomes negative. And here now, I just divide by 6x. So I did not 6x, I divide by 6y. So if I divide by 6y over here, I also have to divide by 6y over here. Regular rules of equation. What you do on one side, you do on the other. So this 6y here cancels this 6y here, thus leaving y prime all by itself. But notice on the other side now, we could do also a little cancelling. This y here, sorry, this 6 here could cancel this 6 here, and thus that would leave us with negative x over y. Easy does it. Yes, nice answer. And that's the answer that we get. Who would have believed when you differentiate something like 3x squared plus 6y squared minus this minus 10 equal minus 10? You'll end up with something like this. This looks so far-fetched compared to this up here. But yes, that's what implicit differentiation does. I mean, you're differentiating two terms at the same time in a way. So yes, sometimes you impress yourself with what you get. I am also looking at this one here, the possibilities of making the y here alone. It is possible, but it will be complicating our life a little. Because yes, I could see me transposing 3x squared on the other side. So that will leave me with minus 10 minus 3x squared. Then I divide by 3, and then I find the square root. But then we have something very messy on this side over here to differentiate. So yeah, I wouldn't want to do that. I think this was a lot easier. Basically 2 steps. 2 steps and we get that. Right. And that brings us to our last one. I think number 3 will be our last one for today. So again, let's see how this one goes. Oh wow, this one is a little interesting. We have 3xy. This here is a little product rule taking place here. Anyway, we'll address that when we reach there. Right, so differentiating as normal. So the 2 for verifying, not verifying purpose, just for clarity's sake, I will put a 0, just for we to see what happens. So when I differentiate this 2 here, I get 0. Then I go to minus 5x cubed. That will give me 15x squared. Again, I just put this 0 so we would see what happened. But I know that 0 there is not necessary. And I'll take it out in the next row. But just for we to understand that I differentiated this, now I'm about to differentiate this. This is a little product rule. And I call it little because it's 2 simple terms. 3x is actually a function and y is actually a function for itself. So remember how we deal with the product rule. We keep one function for itself. So I have 3x, and then I multiply that by the first derivative of the next function, which in this case is y. But when I find the derivative of y, remember it will be 1y prime, because I differentiated a y term. This is a multiplication taking place here. And then we do plus. Yes, plus. Then we have the second function, y. And we multiply that now by the first derivative of the first function, which in this case would be just 3. So y times the first derivative of the first function, which is 3x, will just give us 3. This might be a little tricky, but I will not go into the details of this. All you need to do is just go back to that video when we did the product rule, and you will understand how the product rule takes place. You have a function multiplied by another function. You leave the first one, you multiply that by the first derivative of the second one, and then you leave the second one as it is, and you multiply that by the first derivative of the first function. And of course, you add both of them. So let us see if I could clean up this side a little. Now I'm getting rid of this 0. So that is minus 15x squared is equal to, and I'm just doing a little, let me see, can I do a little cleaning? Yeah, I could do a little cleaning. So over here now I would have, well, not a cleaning, this one is not much of a cleaning, it's just a little arrangement, right? So this is the same as 3x, I'll leave this just so still, 3xy prime plus, this don't even worth being a step, but 3y. Yes, let's put it like that. 3 times y, or y times 3 is actually 3y. And now I want to make y prime the subject of the formula. So firstly, I'll get rid of the 3y. So I will send the 3y over here. It is positive, so when it goes over, it will be negative. So it will be negative 15x squared minus 3y is equal to 3x y prime. Yes, and to get rid of that multiplication that is understood between these two terms here, all we do now is divide by 3x. So I divide here by 3x to get rid of the x, and because I did this on this side, I do the same thing on the other side. So that is divided by 3x. Sorry about that. Divided by 3x. My nose running a little. Right, and here now 3x cancels 3x, and that leaves us with the golden answer of, and again I just replacing places, y prime is equal to negative 15x squared minus 3y all divided by 3x. Yep, all divided by 3x. And that is our answer. This could actually go further. Should I go further? Okay, let me go further, because yes, I could see this breaking down even further. So let me just take it over here, just continuing on, just cleaning up this a little. So here I have the same thing as, follow me now, y prime. You don't have to, based on what you're asked, but sometimes you might have to find the gradient of a line. So in case of that, let's see if we could go for, we could break down for. So this whole thing here is written can be the same as 15, negative 15x all squared divided by 3x. Yes. And that is minus 3x. So I just, no, sorry, 3y over 3x. What I basically did there is just, I split the denominator, right? So I just split the denominator. If I go to put these two fractions here together, I will end up with what I have here initially, right? So I didn't change anything. I just separated the fractions. And I did this so that you could see the breaking down process easier. So when I do this now, we could easily see that 3, let me put that in red, we could see that 3 could actually go into 15 5 times. So here now I have negative 5, and one of these x could cancel one of the two x's here, so that will leave me with negative 5x. Minus, over here we could easily see that 3 could break out 3 could cancel out with 3, so that would leave us with minus y over x. Yes, and this is definitely as far as we could go. Anything beyond this is actually knowing what is the x value or what is the y value to substitute and then find whatever we were asked to find. So yes, this is as far as we could go. But again, mind you, I would safely say if you reach as far as this, I think you will get full marks for that. Unless the examiner probably tell you go to the lowest form, or I would go even further by saying if you were asked to maybe find the gradient of a line, or if you were asked to find the equation of a certain point at a curve, something like that, maybe I would encourage you to go all the way if possible. But if not, ending right here would be just perfectly fine. So this will bring us to the end of today. That's implicit differentiation for us. So again, as always, feel free to like this video, share it, and subscribe it to persons that you believe this would be very helpful to. And in the next video, we're going to go into some simple logarithmic differentiation. As usual, we're going to just look at the concept, and then we're going to look at various components. I think that series will have either 4 to 5 parts, because I'm planning to do each one separately, each logarithmic rule separately, but it will all fall under logarithmic differentiation. So again, thank you very much. You do enjoy the rest of your day. Take care, and until later.